Hi, my name is Klaartje De Weerdt, and I'm a professor at the Norwegian University of Science and Technology. In connection to the Robert Lermite Medal I was awarded this year, I took the opportunity to write a short paper on chloride binding in concrete. So why chloride binding? Well, I live and work in Norway, and here we have a long coastline, which means that many of our reinforced concrete structures are exposed to seawater, which contains chlorides, such as this bridge. In addition, we have long and cold winters, where we use chloride salts during winter maintenance on, for example, roads. So many of our reinforced concrete structures are exposed to chlorides and are thereby prone to chloride-induced reinforcement corrosion. What happens is that chlorides from seawater or the icing salts penetrate the concrete cover, and when they reach a sufficiently high concentration in the vicinity of the steel reinforcement, they'll cause corrosion. And it's this corrosion which will reduce the load carrying capacity of the structure and might lead to failure. So corrosion of steel reinforcement costs our society a lot, both in repair costs, but also potentially in having to demolish structures and build new ones. If you want to know more about steel reinforcement corrosion, I advise you to look at the talk from Ole Angst, who got the Robert Lermite Medal 2 years ago. In this talk, I'll talk about the chloride penetration in the concrete cover, where chloride binding plays an important role. Imagine you're an engineer and you're responsible for the maintenance of a reinforced concrete bridge, which is exposed to chlorides. One way you can figure out how far the chlorides have penetrated into the concrete cover is by extracting a concrete core, profile grinding it, so you get dust at different depths from the exposed surface, and analyzing this concrete dust for its chloride content. If you then plot this chloride content as a function of the depth where you've collected the dust, you get a chloride profile, as you see here. This is a chloride profile which I obtained from a concrete which was exposed, submerged to seawater for 16 years. And we can see that the chlorides have penetrated the cover and have come as deep as approximately 40 millimeters. You can use these chloride profiles for something else as well. So an engineer can use them to try to predict how long it will take until you have a certain probability for corrosion. And we typically use empirical models for this. So, for example, the model described in the FIP model code or in the ISO standard relies on an empirical model. So what we do is we fit the error function solution from Fick's second law through the chloride profile, and you obtain some fitting parameters such as a surface concentration and an apparent diffusion coefficient. The challenge is that these empirical models, they rely on long-term field exposed data, such as these chloride profiles, in order to be reliable. This has been actually quite fine if we are working with similar binders, but that's the challenge, because as you all know, cement production stands for about 5 to 8% of the man-made CO2 emissions, and we need to do our best to try to reduce them as much as possible. One way of doing that, one fast and very efficient way of doing that, is by replacing part of the Portland cement with supplementary cementitious materials, or in short, SCMS. So cement industry has been doing that for the last 20 years. So the challenge is that we're running out of the conventional SCMs, such as fly ash and slag. So we urgently need to start using new SCMs, which have a different composition, different reactivity, so they will affect the chloride ingress resistance of the concrete. And then we don't really have the time to obtain long-term field data for these empirical models. We actually really should start to use mechanistic models that actually can cope with the variability of SCMs we're going to have on the market soon. So for these mechanistic models, that's where chloride binding is a very important aspect. So chloride binding would, for example, in this chloride profile, refer to how much chloride can be bound to the height of this little rectangle, which is drawn here. Besides chloride binding, of course, SCMS will affect the porosity and the permeability of the concrete as well. And that will also be very important when trying to model chloride ingress in concrete. So we won't deal with that in this talk. This talk will focus on chloride binding. When we talk about chloride binding in concrete, we're actually talking about chloride binding in cement paste, because we consider the aggregates as a non-reactive part when it comes to chlorides. So in the cement paste, we have specific hydrates that are known to be able to take up chlorides. And one family of them is the RDFM hydrates, so the aluminum ferrite monohydrates. One of the most known ones is Friedel salts, the chloride containing AFM. And the chloride is there taken up in the crystal structure. It's actually in the interlayer. So it's part of the structure, and that's why we call this chemical binding. In the case of calcium aluminate silicate hydrate, or in short, CASH, the chlorides are not really taken up in the structure, but they're more absorbed or attracted by the surface. And this we refer to as physical binding. And finally, some of the chlorides will be found also in the pore solution, which we often call for free chlorides. So what I'm going to talk about in this talk about chloride binding is going to show some of the most recent research results we've obtained and focus on the knowledge gaps. Where do we have to focus our research efforts on in the near future to actually get these mechanistic models? So before diving into the research results, it's important to note that we mainly have used equilibrium tests to determine or to understand chloride binding. And in these tests, we have put hydrated cement paste in contact with chloride-containing solutions in a closed container, and that tends to equilibrate, shaking them sometimes. And then when we've reached equilibrium, we will analyze the pores or the solution and the solids and try to understand how these two interact. In the first study, we looked into the cation effect. The cation is the positively charged ion which combines with the chloride in the salt. So in this case, this is magnesium, calcium, or sodium. This effect is known that the cation plays an important role in chloride binding, though the explanations for it are vary widely. So in order to understand chloride binding, one typically determines something which is called a binding isotherm. On the left, we see binding isotherms. So in the binding isotherms, you plot the amount of bound chlorides per gram cement paste as a function of the chloride concentration it's exposed to. In this case, the chloride concentration at equilibrium. And you can see that we expose the cement paste to a range of chloride concentrations. So we go from approximately 0.25 mole per liters up to 2 mole per liters. Typical chloride concentration for the Atlantic Ocean is about 0.5. So it means that, for example, 1 or 2 mole per liter are high concentrations and are more relevant for example, the icing salts. So what we can see from this graph is that for sodium chloride, we are in a way for all these concentrations on a plateau. There's not a large difference in the chloride binding depending on the concentration. Whereas in case of calcium and magnesium chloride, we see a considerable increase when you're increasing the chloride concentration. So why do we have this difference between sodium chloride and calcium and magnesium chloride? So we used the thermodynamic model to predict what was going on into the system. So we used GAMS. I'm not going to go in detail into these figures, it would take us too long, but these figures actually illustrate what the thermodynamic model does. It predicts the hydration phases that are formed in equilibrium with a solution. So it calculates the composition of the solution and the amount and composition of the hydrates formed. And if we look at the binding isotherms where the model predicts, there's actually not a large difference between sodium chloride and calcium and magnesium chloride. They're rather similar. So the thermodynamic model is not able to capture the difference we observe experimentally. And the reason for this is that thermodynamic model actually predicts chloride binding in chloride AFM or Friedel salts. So it doesn't account for whatever chloride absorption in the CSH. And that for us gives an indication that this difference might be due to CSH. And something which is, so this is quite difficult to test experimentally. We've tried, but we have some challenges with sample preparation in order to determine this with some ETS. So we tried to look at this indirectly by looking at the exposure solution. And when we analyze the exposure solution, we see a clear decrease in the pH in the case of calcium and magnesium chloride exposure. With these two salts, the pH drops considerably when we're adding more chlorides. In the case of sodium chloride, the pH varies much less. So this decrease in pH in the case of magnesium and calcium chloride is associated, according to the model, with an increase in calcium concentration. And it's this increase in calcium concentration which actually can increase the capacity of the CSH to attract chlorides. So according to the electric double layer theory, CSH surface is negatively charged and it will attract calcium ions, positively charged calcium ions in the stern layer. If you have a higher concentration of calcium, we'll be able to attract more, or we will have more calcium in the stern layer. And then in the diffuse layer, this positively charged calcium ions will attract on their turn negatively charged chloride ions to charge balance. So we will have an accumulation of chloride ions in the vicinity of CSH. So what we're seeing here matches quite well with the ideal theory, though this remains to be confirmed experimentally. Another thing we saw in the study is when we plotted the amount of bound chlorides as a function of the pH, we got a nearly linear relationship. So this, of course, is only a limited amount of samples and it's only one cement composition, but we could see that the amount of bound chlorides seems to increase when the pH decreased. And that triggered the idea for us for the next study. So in this study, which I performed together with Peter Hemstad and Alisa Machner, we tried to play more with the effect of pH on chloride binding. So we call this the effect of leaching or acidification on chloride binding. What we did is we started with sodium chloride and a calcium chloride binding isotherm, as we've seen before. But now we took a sample from the sodium chloride isotherm and we started gradually adding hydrochloric acid. And our hypothesis was that as we in that case are decreasing the pH, you would have an increase in chloride binding. So we are adding hydrochloric acid to our system. So at a certain point, we will start dissolving chloride binding phases. And then we would expect a drop in the chloride binding. So this was our hypothesis. And then we made the setup. And our experimental results confirmed exactly that. So we see when we're adding hydrochloric acid, we first get an increase in chloride binding, and at a certain point, a decrease. So if we look at these experimental results, but we plot them slightly differently. So we plot the amount of bound chlorides instead of as a function of the chloride concentration in a function of the pH. And what we see then is that the chloride binding, when we start at a pH of 13.2, when we start to lower it, first the chloride binding increases until a certain level, pH around 12, and then it starts to decrease. This pH around approximately 12 is also the pH where we expect in the system that the portlandite will be dissolved. So then our system starts to become calcium deficient. So our aim in the study was to explain, so we have proven this pH dependency of the chloride binding, but what is actually happening with the hydrates? Can we explain this behavior by changes in the hydration phases? Peter determined the amount of chloride AFM using TGA, and he determined the chloride content of the AFM using SAM-EDS. And if we can see that the amount of chloride AFM actually follows a bit the trend of the binding isotherm. And we also see an increase in the chloride uptake of the AFM when we're decreasing the pH. So if we combine those two, we can see that the AFM is contributing to this peaking behavior you see in the chloride binding, but it's not explaining the whole thing. So again, our hypothesis is that this the part we can't account for might be due to CSH. Though this remains to be proven experimentally, and this is quite challenging because the CSH content will change and the composition will also change quite drastically in this experiment. So even though we haven't answered all questions, these results are very interesting and very relevant even for the engineer responsible for maintenance, because what we're seeing here explains something we see in the shape of chloride profiles. When a concrete is exposed to seawater, the outermost section will leach severely. So there we might expect a pH of approximately 9 or 10. And there we see we will have a reduced chloride binding. Whereas slightly deeper into the concrete, we will have a more moderate leaching. So for example, a pH around 12. And in that case, we will have an enhanced chloride binding due to this moderate leaching. This explains a little bit the peaking behavior we see in chloride profiles, where we see a lower chloride content at the surface and a slightly higher chloride content a bit deeper into the concrete. So highly relevant. So important is that all these results up to now were done on Portland cement. We haven't used an SCM yet. In 2 other studies I contributed in or was part of, we looked into the impact of SCMs. Senghor Shi in his PhD thesis and Arizu Baba-Ahmadi in her postdoc. They both used Portland cements as reference cements and tested exposure both for sodium and calcium chloride exposure. They tested the impact of metakaoline from 15% to 32% on chloride binding, and we can see a clear increase. All these green points are above the reference. We have an increase in chloride binding. This has been observed before, amongst others by Zipaira. When we add silica fume to the system, for example, 15% silica fume, we see a similar or decreased chloride binding. It's also some chloride exposure. They tested the impact of metakaoline from 15% to 32% on chloride binding, and we can see a clear increase. All these green points are above the reference. We have an increase in chloride binding. This has been observed before, amongst others by Zipaira. When we add silica fume to the system, for example, 15% silica fume, we see a similar or decreased chloride binding. It's also been observed before. And then interestingly, Arizu, she combined metakaoline, so 15% metakaoline with 50% silica fume. And we can see that the silica fume is actually cancelling out this beneficial effect of the metakaoline on the chloride binding. Now, if you want to explain how these SCMs are affecting chloride binding, you really have to have control on your phases. So I'm not going to go in full depth of these 2 studies, but in both studies, we encountered challenges as we didn't fully, similar in the previous studies with the Portland cement, we didn't fully quantify the amount of AFM, check the composition, and the same with the CSH. We didn't fully quantify the CSH and determine the composition. So if we want to say something about how an SCM is affecting chloride binding, we actually really have to determine the amount of the phases formed and their compositions. And preferably, this would be in such a generic form that we can make models out of this. So this brings us to the second part of the presentation, which is knowledge gaps. Let's start with AFM. So on the modeling side, for example, thermodynamic modeling, we have some really nice data from Balonis et al. For chloride AFM. She got full thermodynamic data for Kusel salt and Friedel salt. Though we could elaborate on her work because there's potential to elaborate towards carbonate deficient systems. And we could do the similar approach as what she used on, for example, hydrotelsite and stretlingrite, as these 2 phases have proven to have similar binding potentials as Friedel salt. And these phases are more likely to occur in some composite cements. So they will gain importance in the future with these new SCMs. So we should get thermodynamic data on these phases. So this is on the modeling side briefly, but also on the experimental side, as mentioned before, there are quite some challenges. In the studies I've presented from our group, we've used TGA for quantification combined with SEMI-DS, which gives information about the composition. So there are quite some loopholes here as well. And recently there's a paper published by, give it some space, by Thuy et al. From EPFL. There's also Ave and George have been involved in this research. And they presented a very promising approach where they use XRD read field to determine both the composition and to quantify the chloride containing AFM. This is very promising but a challenging technique. So in real cement systems, quantifying and looking at the composition of AFM is challenging. And then we come to the black box, CSH or cash. In literature, the interaction between CSH and chlorides is often described using the EDL3 theory, which I described earlier when I wanted to explain the cation effect. So recent advances in chloride in modeling of CSH on an atomistic level are showing very high potential to start to know more about how the chloride actually interacts with the CSH. What are the forces working on the chloride? Would it at all? How does it contribute potentially to diffusion? And there are several research groups around the world that are working with this and that have promising results. Here's just an example of one of them. These are two of my colleagues from SINTEF, Svenum and Ringdal, who within the Rosenus EU project have worked on this topic. So I think that this is a very promising domain where we should really invest. Then on the experimental side, a little bit more what I work with, CSH is also very challenging. We can determine its composition in a cement paste using, for example, SEMI-DS, though there are challenges in sample preparation. And we not only need the composition, we also need the amount to be able to say how it contributes to chloride binding. And there's also quite some challenges to determine the amount of CSH in the system. Now, if we have a better grip on our AFM and similar phases and on our CSH and are able to predict chloride binding in these phases, this should be included in numerical transport models. There's an example here of a recent one published by Michael, but there's a handful of good multi-ion transport models. For more information, look at the paper. One thing I would like to say here is that it's important that these codes are made accessible so people working with binding can contribute, and the engineer responsible for his bridge can look into it and try to see what he can use. So we need to work together with transport modelers. So to conclude my talk, where do we actually want to end up? What is the ultimate goal? This figure is a little bit an illustration of it. It's not fully there, but close to it. It's work done by Alisa Machnir in her postdoc within the Chloride project. And what she did here is she determined the amount of AFM and CSH using thermodynamic modeling, and she but she measured with SEMI-DS the chloride content in these phases. And when she combined these two, she was actually able to reproduce the shape of the chloride profile of the mortar where the chlorides had ingressed. So what this figure shows that if we understand chloride binding, here it's measured, but even better if we can predict it, we can better understand chloride profiles, why they look the way they look, why they change because we're adding SCMS. And this will be a great step forward to understanding chloride ingress with concretes with new binders. So this is in a way the overall goal is to work towards mechanistic models which we can use to optimize concrete, both with regard to durability and sustainability. We can actually get the best out of this wonderful material. So this brings me to the end of the talk. It remains me to thank, first of all, the jury for awarding me this. It's an incredible honor to get the Robert Lemaitre Medal. I really have to thank my supervisors for all the support and all the opportunities I've been given on the way. Without them, I wouldn't be here. All my colleagues at CENTEF and NTNU, and collaborators in industry and postdocs, PhDs, and my master students, which I've been doing all this work with. It's been wonderful. Also, thank you to family and friends for coping with my slightly out of proportion enthusiasm for concrete. So, thank you for your attention.